All right, there'll be a couple of small files there when I look at the recordings. So today, welcome everybody back to the machine learning on OpenShift SIG. And my name is Diane Mueller. I'm the co-chair of this semi-regular SIG meeting. And today we have a couple of speakers lined up to talk about MLFlow and an MLFlow operator that's being worked on. If you have a chance in the chat, there's a link to the meeting notes that you can see on your screen right now. You can add that. If you can add your name to the attendees, that would be great. As I was mentioning before I hit the record button to Manny and Zach, one of my goals for this is to see what the next steps are in terms of the MLFlow operator. So I'd like Manny to give and take the screen over now and maybe explain what MLFlow is, give us some context for that, and then Zach, who has been working on an MLFlow operator in his own repo to get that work moved into a space in the MLFlow repo that other people can collaborate and work on with it and maintain it over time, if that's the appropriate thing to do. That's kind of what I'm trying to suss out today too. And for those of you who don't know, yesterday we launched something called operatorhub.io, where there's about a dozen now, one day in, operators that run on Kubernetes generic standard stuff, and as well as on an OpenShift. So it's not an OpenShift centric hub, but I'd love to see an MLFlow one in that hub as well, sooner than later. So Manny, with that, how about if you introduce yourself, take over the screen, and let's hear a little bit about what MLFlow is today.
Perfect. Can you folks see my screen?
Yes, I can. Okay, just make it full screen and it'll be perfect.
Yep. Let me go into presentation mode.
And that's perfect. Thanks, Manny.
Perfect. All right. Hello, everybody. Good morning. My name is Mani Parkhe. I am an engineer at Databricks working on MLFlow. So I'm here to talk to you all about what is MLFlow, the motivation behind building this machine learning framework, what the components of MLFlow looks like, and where we're going to take this. So I'm going to introduce all of this in the next 15 minutes or so as a preamble to Zach's presentation. So anybody, I'm sure this team appreciates how complex MLFlow development is, and also appreciate that it's slightly harder than traditional software development as we have done in the last few decades. Sort of to tease this out a little bit, I wanted to sort of talk about some differences between traditional software development and machine learning development. So let's start with problems in each. So let's say you take a problem in traditional software. Let's say you're building a credit card transaction system or a functional verification system or any of that. You start with a functional specification. You know exactly the terms and conditions and what product you're trying to build. So the goal is pretty clear what you want to do. In machine learning, the goal is to optimize the metric. So there is no perfect answer. You're just trying to get better and better. The metric could be increasing accuracy, or it could be a vector of different metrics that you're trying to optimize. All right. The other difference is quality. In traditional software, when you're trying to solve a problem, the quality of the product eventual depends primarily on the code, which includes obviously the unit tests that you write and integration tests, but primarily the code that you have that engineers write and test, and yeah, to some level on the system. So that's pretty contained of a problem. When we go to machine learning, there's not only all the code and the system, but also the data that we use for training the models, and then how well the model is tuned, and how we regularly continue to update with fresh data, and may have to tune the models, use different algorithms, and so on and so forth. So the quality is sort of a shifting goal and a moving target, just like the goal that we talked about. And the third thing I want to talk about is in traditional software, you develop off of a common software stack, something that the team is flexible, has worked with in the past, released different projects on. You're pretty well acquainted. Machine learning, on the other hand, you want to constantly experiment with newer libraries that constantly keep coming out, different frameworks, new algorithms, various different types of models. And not only that, other than experimenting, you must know how to productionalize them. So just having a model that is built with this new framework is not good enough. You need to know how to productionalize it and put it into in a serving fashion in your existing framework. So that sort of becomes hard. Um, let's look at the same thing slightly differently from the machine learning lifecycle and how all of this presents challenges. A typical machine learning life cycle always starts with taking in raw logs of some format, and then they're ETL'd and cleansed, and then you featureize them to get some feature vectors. And then you train it using different training algorithms, serve it, and then monitor how the serving looks like. And this looks simple enough, but it's not, because eventually there are these backward loops. For instance, after you sort of train your model, you realize that, okay, the feature vectors were not perfect, so I need to go back and redo those. Or you might have to retrain with another algorithm. Or if the model looks good, it's productionizing the production logs, it's going to create even more data that you might want to bring back into the loop and retrain for the next iteration of this model. So by itself, even if this looks like a straightforward loop, it has its own iterative loops built in. Now let's say you go ahead and try and implement each of these steps in as a machine learning lifecycle. You'd realize that there is a zoo of ecosystem of frameworks for each of this. Your logs could be coming in from Kafka, and you may be using Spark to do all the heavy hitting and cleaning of data featureizing. And then there is TensorFlow, traditional machine learning algorithms like scikit-learn and so on and so forth to train the data. And then you have all of these different frameworks where you can deploy that. So using all of this can sort of present all its challenges. And typically for machine learning practitioners, it is incentivized to use different algorithms and different frameworks in order to best receive, to get the best quality that we've been talking about for your model. So if optimizing metrics is the goal, then you pretty much end up trying out various different tools. And to add to that, just being able to train and create a model is not sufficient. We all know that using the right parameters for tuning is quintessential to getting the right model. It can make all the difference between just guesswork versus using the right set of parameters to get the ideal results that you've been looking for development of the product. And beyond that, as we talked about, deploying of these models and managing the life cycle of each of these models becomes a challenge in itself. Now, to add to that, if we sort of add to the next layer, as the team starts growing bigger, as the amount of data gets larger, scale adds up. And you end up having to deal with various different people and different teams owning different components of this life cycle. So you may have a team working on a team of data engineers working on the ETL and logs part of it, and a set of data scientists working on the training aspect, and a set of system engineers on the deployment part of it. So you have to sort of work through the life cycle of a model, how it passes through these different teams, and governance of it all. And then finally, building a model and putting it in production is one side of the problem. Working with the rest of your product, whether it is a fraud detection system or ad click tracking, you want to be able to use other systems in your ecosystem that work along with your machine learning models. For example, you may want to A/B test different style of models, or you may want to sort of track how these experiments are flowing through different life cycles of the user, or you want to sort of have a more automated, orchestrated way of training these models and managing lifestyle. And finally, you have to start worrying about how the models drift from their expected quality and data drift and so on and so forth. So this in itself, what we have seen is an extremely complex process. There is not a single tool out there that makes it easy to use. And in fact, you have to end up using multiple tools that you and the team are comfortable with, right? So as we start looking at this, when we built MLFlow as an open platform to be able to, for users to manage their models and machine learning frameworks, we wanted it such that it works with all of these existing tools, makes it easier to work across the stack of these various tools, and not necessarily be one of these tools, but work with a lot of these tools to solve the problems that have not been solved. So going over to stuff, if I have to talk about what is MLFlow in a quick 3-bullet slide. So MLFlow is an open platform that helps you manage your machine learning development lifecycle, and it does it in 3 ways. One, we have lightweight API to be able to work with any ML library. So as we talked about, as like everybody has their favorite library to use, or in fact, you want to try out different libraries. They could be in different programming languages. The key aspect that we saw here was data scientists and machine learning practitioners don't want to get locked in to one particular library or one particular language. You want to sort of be able to use any kind of language. So that's where we built MLFlow as an API-first approach. So you can talk to MLFlow as components using REST API or Python, Java, and R. They're all built up on this basic REST API and lets you interact with MLFlow. The second thing we wanted to do is we wanted to make it make reproducibility of the runs a primary. So for instance, you typically train your model on your local machine, and then you want to sort of make sure that it reproduces the exact same results when you're running it on a cloud somewhere, any kind of cloud platform. What makes it hard is get that reproducibility in. If you send your code to some other engineer on your team, they should be able to do it the exact same way. So having your ML sessions run the exact same way on any cloud was one of the other development principles, key principles behind building MLFlow. And then finally, simplicity and ease of wrapping up was the other goal, such that it should be useful for one engineer on an org, but also easy to scale up to 1,000 people org. So the scale and ease of use was also sort of thought in when we sort of designed that. Okay, so from here, MLFlow supports like 3 different components to begin with. One is the MLFlow tracking server. We're going to spend some time talking about that. It's necessarily a centralized repository to store all the critical information that is generated from and required to generate your machine learning run. And this could be like the parameters and configs and also the metrics that come out, right? So that's that, and then it has mechanisms to query that. So it's like a database for all your machine learning runs. The second one, MLFlow projects, is a code packaging format, and that is targeted towards making your runs reproducible when you run it on any cloud platform or at any point of time later on. So this is a way to sort of store everything such that you can guarantee that you are reproducing that runs and anywhere, and anybody else can do it as well. And the third one is ML models is a generic format, a packaging format for models, such that the models that are once written out by MLFlow can be deployed across a variety of production platforms, may it be in real-time scoring format, or it could be like batch scoring or streaming platforms. So that's the 3 big components, and then I'm going to spend a few minutes talking about each one of these. So let's jump right into the key concept of tracking, MLFlow tracking. We talked about tuning machine learning, your algorithms. So parameters, which could be like a numeric or string parameters, are key to sort of making sure you get what you want out of your machine learning run. Data scientists sort of try out thousands of experiments with a same algorithm to sort of get the right right results that they are looking for. So one of the key concepts is a dictionary of parameters that might be associated with your particular run. Another thing is after your run is done, you generate numeric values by scoring your on a test data. So what are the metrics like accuracy, error, so on and so forth? That becomes a key concept that the tracking server might want to, the engineer might want to keep track of in this consolidated repo. And then finally, if you start looking at your models, the model generated from your training run could be itself an artifact that you might want to store away to keep track or governance, or even use it for scoring later on. Along with that, you want to keep track of metadata around your metadata around how the model was scored, what source code was used, the exact version, maybe a Git ID, a Git hash. These are some of the interesting things you may want to store around along with your training data. And then finally, there could be some text that you might want to store, a document that might want to capture the details of your model. And for that, we have this high-level tag or notes that you can record for your training run. And then at the bottom right, you see a UI that sort of shows how it would show up on an MLFlow UI. This is the query layer that I was referring to, where you have an ability to show all your runs and then using this a SQLite syntax query that run for metrics and parameters and sort of slice and dice your data based on specific metrics. For example, you can say metrics.accuracy is greater than 0.98 or so on and so forth. Okay, so how do people use this consolidated storage? So your MLFlow tracking server, as I said, is a database, and you could have various people writing to this database for each training run, either through some hosted notebooks or a local app running on your machine or a cloud job, right? So they're writing to this centralized database through REST API or Python API, and that's how they're storing, as we'll see how it is done. And then we have built a UI layer, and then there is an API layer to be able to query that database. So in this picture, we sort of abstracted away the database. We started off when we released MLFlow using a file-backed store, and now we have various different stores. We'll soon be releasing a SQL-based store to sort of store all the metadata around runs. And so you can query that using, again, as a UI that we've built, or using Python API. All right. Now, finally, how does this look like? The lightweight API I was talking about, it starts off with very simple. You start a run, and then you can record the parameters that are super important for the particular run, and you can see that highlighted in green here. And then you can paste in your training algorithm, and at the end of it, you compute some metric based on some test data, and you can log that metric, or you can actually log the artifact or some higher level you can log the model or some high level artifact, like for instance a plot of some metric data, and that can be logged as well. And then in this particular example, the model happens to be a TensorFlow graph. So we are logging it like a TensorFlow graph. So MLFlow has these packages within it to understand that, hey, this is a TensorFlow graph, I'm going to write it as a model. So any kind of tool that understands the TensorFlow graph can use that for deployment. So with very simple API that surrounds your existing training algorithm, you can now very easily use a tracking server, and whatever happens during this run gets logged to the tracking server. All right, so that was tracking. Now let's talk about projects. Now, as a reminder, this is again a mechanism, a packaging mechanism to make it easy for you or anybody on your team to reproduce your runs on any cloud platform anytime later. So what are the things that we need to be able to do that? So in this packaging format, we obviously need to include the code that is needed for training. You may also need some configs and some pointer to data. So this effectively constitutes what would be needed to be able to reproduce the run, whether it is running it locally on your or somebody else's local machine or running it on some remote cloud. But then how exactly does this packaging format look like? So here's an example. It's necessarily a directory structure where you have this file called ML project. And if you look at the file, here's an example of a very small version of the file. It right at the bat tells you that it needs a conda environment, right? So this is the conda environment that the data scientists use to train their model. And the conda is a YAML file that is included within that directory structure. And then if you look at the next thing, it talks about one entry point, a main entry point for being able to run this project. And it says that, okay, you need these parameters, which is a path for the training data and a float parameter called lambda. And here it's defined as a default value of 0.1. And then how does MLflow know what to do when it sees that entry point? It says, okay, it runs a very simple Python command called main.py, and it gives it the training data in Lambda. And obviously, this is the code main.py, and then there could be other dependent modules included. That this is the code that you have written to create your training run. So very simply, when you write a training algorithm, you include this within that directory structure, create a simple ML project file, and capture your conda environment, and boom, anybody is able to then reproduce your run using a simple couple of MLflow commands that can just take your existing code, use their data, use their parameters, and create a run, or you can reproduce your run. So how does somebody do that? Through a command line, MLflow space run space a GitHub repo, or it can be a link to this local directory structure. If you want to do this programmatically, there is a mlflow.run, a Python command to do that. So with a bunch of cluster specifications, you can run this on a cluster as well. So very simply, you can sort of do all your local training, package it up in this format along with a conda environment, and then you're set to go to run this on the cloud. And then finally, to talk about models. Models, again, was a format that once you write out a model using MLflow models, it should make it easy for you to deploy this on any kind of an environment that can host that model. So let's take an example where excuse me, where you have created a model, and it could be like a TensorFlow graph model that in your local environment, and then you want to write it out in such a format that it can be loaded on, let's say, Amazon SageMaker, and then also in some kind of environment that runs Python. So this would be a way of saying that the same model that is used by one team for, let's say, batch scoring is also used by another team for some real-time scoring. And it uses the same model that is being written by MLflow. So how does this look like? Again, this is a packaging format. The format will be very similar to what you've seen in projects. It is an ML model file, and it has a few things. First, it tells you a few metadata about when this model was created, what was the run, and then it says that, okay, here we have this model written out in two different flavors. One is a TensorFlow flavor. That's a dictionary of things that any environment that, that can run a TensorFlow format would need to be able to deserialize this model and make it executable. And then any environment that uses Python can use this ML flow module called MLFlow or TensorFlow to be able to then load this module and then execute it like it would with any Python function. Again, it all depends on making sure that all the dependencies are in play. So now if you have a team of data scientists, all they need to know is how to load, run their own training and package the model using the MLflow commands, and then at the end of it, you could have another set of system engineers who can easily take these MLflow written models and deploy it onto any framework that makes sense. So MLflow becomes that central place where users can use to sort of create various different deployment frameworks, deploy to those, write it, and all that. Okay. So how can you learn about a little aspects? This was a little flavor of how MLflow looks like. There is a lot more in terms of documentation and training examples if you want to do some hyperparameter tuning, multi-step workflows for REST and batch scoring. You can start off with installing MLflow through Parkhe, or you can download it through the GitHub repo and try it out. So the key point to go to would be mlflow.org that hosts a website and has all the examples. Okay. In the last few minutes, I want to just talk about the open source community growth and how MLflow that started off about 8 months back has been well appreciated and embraced by community. So this is a quick, I wanted to use 4 metrics to sort of show that. It started 8 months ago when it was released during Spark Plus AI Summit in June. And since then, we have 77 code contributors from 40 different companies that have contributed to it. And here's a quick plot that shows about the number of contributor growth over months as compared to a couple of other favorite open source projects. And across, and this is a great chart that shows how quickly people have started using it and actually writing code and contributing different things. Another metric that is amazing is about 420,000 monthly downloads on Parkhe. Again, a comparison with some of the other favorite tools that people use. So this is about this is great growth in the last 8 months or so. We have a San Francisco Bay Area MLflow meetup. We have about 718 members, and here are some pictures of one of the latest meetups that we had here at Databricks office, and some folks from our customers and other people showing how they've used MLflow and in their workflows. And then finally, we recently had a survey on mlflow.org website, and 30 orgs want to publicly list themselves as users of MLflow. And I want to sort of state that this survey is still open, and I invite everybody to go look at mlflow.org, and there's a Google form for the survey. We want to know if you have used MLflow, and if you have not, what sort of things are you looking forward to in that. I want to know more about what makes what are the requirements that you're looking for, and what would make it easy for you to use MLflow. So at a very high level, some of the large contributions to MLflow came from external orgs. It could be system-related things like Git integration and cloud support, or UI level of work to visualize experiments and integration with different packages. A lot of contributions came from external contributors, and these are some of the big ones. And there's way more than this. This slide is slightly dated. In the last few minutes, I wanted to talk about roadmaps and where we are sort of going from here. As I mentioned that we had this survey, one of the things in this survey was, how have you been using MLflow and what would you like to see more? So one of the things that we heard was that we wanted to that users had a lot of requirements for existing MLflow components. To name a few, currently we are at version 0.83. and we want to sort of, as we start going to 0.9 and 1.0, we're sort of thinking of adding, in 0.9, we'll be adding a SQL-backed store for tracking server. This is one of the most frequently asked requests. And then we're adding Fluent Java and Scala API, a lot of UI scalability, enhancements, and then more on the logging side of things. For projects, we talked about Conda being used to reproduce your runs. There has been a lot of ask for Docker-based project environments. And then finally, I want to mention in MLflow models, a lot of requests came around that, okay, I want to use a model, I want to save it, and then I want to sort of inject some custom code. It could be sort of querying from a feature store, or it could be like, transforming features a little bit. So the sort of custom logging and custom code is something that is being worked on actively, and we'll start releasing it in 0.9 and 1.0. This is some of the things that are on the roadmap for the next few releases. But then we are also starting to think of some more components that we could add. For example, a model registry or a multi-step workflow using GUI. You can already do that using the ML projects, and you can have multiple entry points. But would it make sense to have a UI to sort of edit your multi-step workflow? And then we're looking at adding some telemetry components, logging data and metrics and taking it back into some analytics tools. So we're looking for feedback around that. So again, another plug for the survey on MLflow.org. We want to know how you use your MLflow libraries and frameworks, and what would you like for us to add as integrations in MLflow. So that's the survey. Thank you all for your time. I want to just sort of, again, put out MLflow.org, join us on Slack, or there's an email thread you can join. And thank you for giving me the time to talk at the summit. If anybody wants to come to Spark Summit, here is a code that I wanted to sort of share with you all. If you have any questions, I'd be happy to take them now or towards the end of the talk. Also, if you want to just reach out to me, I'm at Databricks. My name is Manny, M-A-N-I. You can reach me at Manny@Databricks or through Slack on MLflow.org. Thank you.
Well, that was great, and a great overview too. Quick question: what is the dates for the Spark AI Summit?
It's in April, if I'm not mistaken. It's April 26th.
Cool. Awesome. I'm sure we'll have some people there from Red Hat for sure. So next up, if there's no questions, or maybe we'll save the questions for after Zach's demo too. Zach, if you want to take over sharing the screen, we will get you set up. And Manny, if you could add into the notes the link to your Bay Area meetup too, because I think that would be of interest for folks.
Yes, I'll do that.
Perfect.
So can everybody see my screen?
Absolutely, we can. Go for it.
Perfect. Okay, so my name is Zach, and I wanted to give an update on some open source work that I'm working on around MLflow operator. And just trying to share some of our use cases and motivation of why we built that. So we had a requirement, and our use case was to basically find a tool to perform hyperparameter tuning. So you might ask, what is hyperparameter tuning? What are these things called hyperparameters? As Manny pointed out in his presentation, when we're creating machine learning models, we'll be, we may want to do some hyperparameter tuning, right? So when we're creating ML models, you'll be presented with different ways on how to define your model architecture. In the beginning, you don't know what the optimal architecture should look like for your model. you would need to do multiple runs and test your model with multiple different different parameters to find the optimal model architecture. So the parameters that we define, the model architecture, are called hyperparameters, and the process of searching for the ideal model architecture is called hyperparameter tuning. So let me tie this back up to the use case here. So applying this to our use case, let's say if we have an unsupervised machine learning problem or machine learning technique such as k-means. So you might ask, what is k-means? K-means is used to partition data points in k clusters, and let's suppose k is 3. Let's say we have 3 clusters, and we have 10 data points. What k-means does is it takes the features of the 10 data points and assigns each point to either cluster 1, 2, or 3. And the data points that are similar will be grouped under one cluster. So when we wanted to do experiment tracking on that particular use case, we were sending performance metrics of our k-means cluster model, such as parameters such as the number of clusters, number of PCA dimensions, and then we were collecting many metrics, but the most important ones for us was the inertia and the mutual information score. So that's more into the use case, but ML lifecycle is a complex thing. We wanted something off the shelf, open source that we could pull in. We're running on OpenShift, which is our distribution of Kubernetes. So we wanted something that runs on OpenShift to do things like this: training the model, doing hyperparameter tuning, versioning. We found MLFlow a great tool that has all these great features, and then tracking experiments. So this is just a GIF. I'll show you an actual live demo of this, but we built an operator, a Kubernetes operator, that deploys MLFlow tracking server, backed by S3, and stores our models and can store our models in Ceph storage. I'll show you a demo today on how you could experiment, track your models, parameters, and metrics, and even artifacts. This is the MLFlow UI. This is Ceph Nano. So just for our demo, I'm just rolling out a Ceph Nano, showing you that you can store your models in S3 in Ceph. So if you didn't want to store, if you want more of a on-prem storage, Ceph is a great technology to try. So I wanted to keep this quick and dive right into demo. So we have OpenShift here. We have our operator here, MLFlow tracking operator. So I've already deployed it. We have one instance of the server, and we have MLFlow here that's already running. So that one instance is there. It's pointing to an S3 bucket called Zach Hassan, and that S3 bucket is here in Ceph Nano. Okay. So what I'm gonna do is I'm gonna run this code here, which is the standard example that's on MLFlow website. But I'll just point you to where the code lives, which is here. It's just a standard example where we're using the standard example, and it's using the same MLFlow APIs. It's logging the parameters, it's logging the metrics, and then it's logging, storing the model into the server. And it's choosing different parameters, and then we can compare these 3 different runs. So let's, without further ado, this is our UI. We're gonna refresh just so there's no smokes and mirrors. we can see there's no runs in there right now. So if I go ahead and do a run, so we already did a build of that Git repo. We built that already. It's already here. We're going to inject a secret, and that secret is here. Since we don't want to store we don't want to ask users for their AWS access key, their secret. We kind of want to keep it in secrets, and then these secrets would get injected into the container. Okay. So let's go ahead and run this. We'll call this OpenShift Commons, and let's go. OpenShift Commons container is running. 1, 2, 3. And let's refresh here. Okay, so we have our 3 experiments. Let's take a look inside. Okay. We can see graphs. We can see our model is stored here. We can see our dependencies here. We can see the format that Manny was showing us. So if I wanted to go actually and maybe pull down this particular model file, I could just go to this S3 address. So I'll just search for the run ID in Ceph storage. I'll go into Ceph storage, find the run ID, artifact, model, and this is our model here. So I could pull that down from S3. But going back into this MLFlow UI. So since I have 3 runs already, I want to say, let's say I want to compare these 3 runs side by side. I can do that, and then I have a UI that I can just compare different runs. I can see, I could take a look at different runs and whatnot. I can compare different things, and I can see them side by side, right? And I can choose the one that provides the best metrics. So that's pretty much the quick demo of running an machine learning job, tracking experiments, storing the model in S3. So just to wrap this up, what's next for this? So the next thing we did was we created a PR in the MLFlow repo. And like all things open source, it always starts with a PR. And we have a PR in MLFlow, and we're contributing this operator to the MLFlow community, and collaborating there. And that's pretty much it. So I'm happy to take questions.
Okay. Well, that's awesome, because you actually answered a couple of questions for me in terms of what the next steps were there. So in terms of getting this into the MLFlow repo and getting it donated there, I'm happy to see that. So thanks, Zach and Manny for making that happen. I'm looking to see if there's any questions in the chat. Not seeing any right now, but what I will do is I will go into chat and unmute people if you would like to ask any questions. And unmuting everyone. You all are now free to unmute yourselves and ask questions. I have one question for Zach about your operator, and that is, is there any dependencies on the OpenShift distribution of Kubernetes, or could this just run nicely on any standard Kubernetes distribution?
So this is using 100% K8 Kubernetes dependencies. This should be able to run on Kubernetes. There is no dependency on OpenShift, but yeah, so it's all Kubernetes stuff.
So what are sort of the next steps that you need? I would love to see this, by the way, because I'm totally biased. And I put the link in there to contribute it to operatorhub.io. So if you can take a look at that link and see if we can get it in there anytime soon, that would be awesome from my point of view. It would give some more visibility to MLFlow and what the folks at Databricks are doing. And I'm just wondering, is this operator, I know it's a hard question to answer, production ready yet, or what kind of feedback do you need before you're comfortable having it in general widespread use?
I'd like to pilot it. First off, get it, probably have more rigorous testing and run it on more different Kubernetes, perhaps certain Google Cloud and other different cloud providers, and to see how have it running there. Probably have some documentation on how to run it on Google Cloud, AKS, Azure, Kubernetes. It should all run all perfectly fine there. It's just I want to try to run it up there. Also, I want to get feedback from the MLFlow community, the MLFlow users, and have them try it out. Maybe run it on Minishift or Minikube, and get feedback there, and then we can continuously improve it and make it better. So I think it should be able to be used today. It should be ready to use today. Perfect.
Well, that's good news. And I think if we can get it into operatorhub.io, and maybe Manny, if we can send an email out to with the videos from today and the links to the mailing list, we ought to be able to get you some more eyeballs on the code base, and maybe you won't have to be doing all of the testing yourself, Zach. So that's one of my hopes here, so we can find other collaborators to work with you and give feedback and log issues and continue to document and tweak this so that it works well for everybody.
That sounds like a great idea.
Awesome. Right, there's one chat in the chat. Let me just see who's got questions. Yeah. Perfect. They're just asking, talking about being able to run MLFlow on Minishift and contribute. That would be great. Hema, if you just unmute yourself, you can ask those questions. See if you should be able to. There you go.
Yeah. Sorry. Yeah. Hi. This is Hema. I'm currently working with the AICOE team. Had a conversation with Zach as well with the different use cases for MLFlow, particularly for the machine learning aspect. As a data scientist, I was testing and trying. So I just had a couple of questions to Manny.
Yeah.
I do know that there are a lot of, like you mentioned, it was great to know that there are new versions of MLFlow coming with some of the features that you mentioned. And the only questions, some of the questions I had was, as I was testing out MLFlow, let's say we have like 3 to 4 data scientists who are working and testing different kind of models. One is running k-means, someone else is running k-means plus or some spectral clustering. So when we run the MLFlow server, which is a one server which is shared by multiple users, is there a way to sort of identify, or if we're all pushing it under one experiment, is there a way to sort of parallelize this, or do we all just sort of push it under one particular experiment ID or give it a name? Is that like something that's already supported, or just wanted to know if there were any further easier ways to sort of understand what are the different people, how the different people are sort of working on the same kind of project?
Yeah, that's a really good question, Hema. So I can answer it a couple of ways. So an experiment, if you start thinking about it, is your way of organizing different runs. So let's say all you 4 or 5 data scientists are working on the same project, and you want to sort of work off of each other's runs. You want to sort of share your data with each other, and they are related to one exact problem that you're solving. Then it actually does make sense to wrap them up as one experiment.
Okay.
And then you all are submitting your runs to the exact same experiment, and then they will be recorded as different different runs that are, because if you look at it, the runs are UUIDs. So you can then have and in the UI they will be recorded with your specific user ID as to who recorded it. So it's very easy to sort of do that. Now, you mentioned a few minutes ago that everybody may be using different algorithms, and that's fine too, because each algorithms may need different set of parameters. They will generate different set of metrics. It might get a little harder to compare across those, but if you really need them all to be together, MLFlow supports that.
Okay.
If you prefer to have them as different experiments, you can just create different experiments and store that. So for example, let's say all of you are working on some ad click tracking or something like that, and you want to sort of have two different experiments for two different class of models, right? Let's say one is a deep learning model and another is a traditional model. You could just sort of like, once you're working on that project for with deep learning, you can record it to a deep learning experiment. If you want to do it for a traditional model, it's going to the other one. So it all depends on how you want to use it. MLFlow supports all of this. As I said, it is designed to scale across a lot of users. In fact, a lot of users that use MLFlow open source have it such that the server is running off of an EC2 instance, the data stored on S3, and a bunch of people, dozens of people in the organization are reporting the data to the same server.
Oh, yeah, thank you. That makes sense. Yeah.
Cool.
I'm just looking to see if there are any other questions. We're almost to the top of the hour, so I always love it when I think I'm giving everybody 15 minutes, but you just blow it out of the water and use the time wisely. So I'm going to thank everybody for their time today, and there's a couple of things that I'm looking for people to add into this the notes here. So if you can link in your slides or send me a PDF version of your slides, I'll send it out to the mailing list as well as posted on a blog on OpenShift.com with the video. And if there's a topic that someone who's listening today wants to talk about at our next meeting, which is on April 5th, please just reach out to myself and again at dmueller@redhat.com or via the mailing list, and we'll add you to the agenda for the next one. So of note, there's a couple of things coming up here. Okay, they're all just thank yous. You're all welcome. I'm really thrilled to host this because I learn something new every day with the stuff that you guys are sharing. So as I mentioned at the beginning, there on March 11th, there's going to be an OpenShift Commons gathering, which has got a number of NVIDIA's coming to talk about their inference work on NVIDIA GPUs and deep learning there. Uber's coming to talk about their M3DB operator, and there's going to also be an operators workshop hands-on in the afternoon in a second room parallel track. So if you're up in the area for that, come for that, as well as I'll add in the link here for the Spark Summit. And thank you, Manny, for the Databricks discount. And if there's any other events coming up, I know there's a few coming just in May. One of the Open Data Science conferences coming as well soon. So hopefully we can sync up because I think that's just before Red Hat Summit. If there's anything else anyone has, I think this was really, very good. Very well done, everybody, and thanks very much. And I'll push the content out, and hopefully we will add some more feedback to both the MLFlow overall project and to Zach's operator as well. And I'd love to see it in Operator Hub sooner than later if we can get there. So Zach and Manny, if you need any help whatsoever on that, let me know. We have a whole little team helping to do coaching for that right now. So now's a good time to get it in there. All right then.
Perfect. Thank you for the invite, Diane. I really appreciate being able to talk about MLFlow here.
Well, I'm happy to have you every time. So We'll do it again when you have another update.
Thank you.
Thank you, Diane.
All right. Thanks, Zach, for pulling us all together. Take care.
All right.